all people in person present and all who are online. So let me start this today early morning session. And welcome, Jean-Christophe. Hi.
Hi.
Yeah, we can hear you definitely and see your slides. So you can start. You are welcome. So your title or title is Gauge Theories on Kappa-Minkowski Spaces, Result and Prospects.
Okay, thank you very much. Let me first thank the organizer for the invitation to present some results we have obtained recently on gauge theory on Kappa-Minkowski spaces. I have a problem. Okay. This is a plan of this talk. Okay. Informally, the Kappa-Minkowski space can be viewed as a universal enveloping algebra of this Lie algebra of coordinate. It has been the subject of a very huge literature for now 3 decades, mainly focused on algebraic property, phenomenological properties which may occur, and also some analysis of classical scalar field theory and their related property. As far as the gauge theory on Kappa-Minkowski space are concerned, the situation is not so clear and a bit more complicated, despite many attempts reported here. There has been recently some advance using the machinery of Drinfeld twist and related objects. There is a nice review on this subject which is given here. And I will not follow this route anyway. I will instead use another star product to describe the Kappa-Minkowski space. Okay. So let me just first summarize the result we have found. First, I will summarize the data we started from. First, we look from polynomial functional in the curvature, which is Kappa-Poincare invariant, and which has some gauge invariance under a non-commutative gauge transformation, and moreover, whose commutative limit is simply a standard gauge theory, a commutative one. Okay. Now recall that the Kappa-Poincare algebra, it's a Hopf algebra, has a bi-cross product structure. Okay. Recall moreover that the Kappa-Minkowski space is a dual of the so-called deformed translation, which are recalled here with the Z generator, and by duality, of course, this factor which involves boost and rotation acts also on Kappa-Minkowski. Now Kappa-Minkowski space can be modeled with an involutive algebra whose star product is given here, involution is given here. Okay. Within this mathematical framework, there is a natural measure to be used to construct action, which is simply the Lebesgue measure. It basically ensures that any action of this form will be Kappa-Poincare invariant. However, the cyclicity of the integral is lost with respect to the star product, and it is in fact a twisted trace, which signals the occurrence of some KMS property. Unfortunately, I will not have time to discuss this during this talk. Okay. This is the main result we have found. We found that any Kappa-Poincare invariant action of this form, it's a gauge theory, is invariant under the following twisted gauge transformation, which are reported here, if and only if the dimension of the Minkowski space is 5. In fact, this is essentially the gauge invariance, which selects, of course, the dimension, but moreover, which selects the unique twisted differential calculus with which all the construction can be achieved. In short, everything is fixed by 2 invariants, gauge invariance and Kappa-Poincare invariance. There are some physical consequences. Some are listed here. First, one predicts the existence of one extra dimension, unfortunately. Assuming some simple compactification scheme on this orbifold, and using some recent data from LHC, one can derive some constraint on the 5-dimensional deformation parameter, which is given here. Okay. One also finds that the dispersion relation for the zero modes in 4-dimensional result, which can be identified with photon, is deformed. It is given here. Okay. This one, combined with some other recent data from gamma rebirth, yields an improved constraints. Okay, with some problem I will try to discuss at the end of this talk. Okay, which would in fact predict a very small size for this extra dimension, which is given here. Okay, and finally, it's a work under study in progress. One expects a very small departure from the usual U1 gauge invariance, the electromagnetic invariance at very low energy. We have currently undertaken this study. I will try to report it in a forthcoming talk, maybe. Okay. Finally, we have tried to characterize the BRST symmetry, which is linked to this twisted gauge invariance. In fact, we have found that it is essentially characterized by two nilpotent BRST operations, which are not independent, but they are continuously related. There is one for, in fact, the gauge invariance of the action, which is in some sense the usual ones, which will generate the Slavnov-Taylor identities, okay, as usual. And there is another one, which is in fact, which gives rise to some kind of non-commutative analog of the celebrated Weil BRST algebra, the one which rules essentially the algebraic theory of anomalies in Yang-Mills theory. And this gives, okay, some very interesting non-commutative version of the horizontality condition. This is only algebra. And we used, in fact, the first one to investigate the one-loop quantum fluctuation, the radiative correction of our gauge theory. And we have found very recently that the one point function is non-vanishing. There is some term like this in the effective action, which simply indicates that the non-commutative gauge invariance is radiatively broken. We have currently undertaken the analysis of possible physical consequences of this phenomenon. Now let me recall some interesting feature of the star product we used in this work. Okay, the star product is simply is obtained from a simple extension of the very old construction done by von Neumann in the beginning of the past century in some attempt to formalize the Weil quantization of the phase space. This is a construction which can give rise to the Moyal product, which is well known. This construction exploits essentially the properties of the convolution algebra, which correspond to the group linked to the coordinate algebra. Okay, the definition of convolution algebra is recalled here, and this symbol is simply the convolution product. Okay, because the coordinate algebra in some sense play a central role, this star product is very natural to consider whenever the non-commutativity is of Lie algebra type. And last but finally not least, it is a star product which is very convenient to use in practical computation in quantum field theory on κ-Minkowski space. I will not have time to comment deeply the general scheme, the general recipe to get such a product. You can extract it from these references, which is quite readable as a mathematical references. Okay, the main point to keep in mind is that it's a kind of matching between the Weil quantizer and the canonical non-degenerate representation of the convolution algebra. Okay. So let me stick immediately to the case of κ-Minkowski. Okay, so one starts from the Lie algebra of coordinate, which is given here, and it is known that it is related to the affine group, which is given here. This group, contrary, for instance, to SU2, okay, is not unimodular. There are two Haar measures, one which is right invariant and another one which is left invariant, and both are related simply by some object which is called the modular function. Okay. In our work, we picked the right invariant measure for reasons which will be apparent in a while. Okay, and whenever this kind of object is chosen, everything is almost fixed. The convolution must be this one, and the involution must be this one. The expressions are fixed. There are no choice, no freedom. Now simply pick the group law for the group, for this affine group here, which is given here, and assume that all the functions here are simply function Fourier transform of other function. You report this in this expression, and you will find, after very simple algebra, a new form for the convolution product, for the involution, while the right invariant measure, the Haar measure, is nothing but the Lebesgue measure. It comes from the computation. At this level, we are almost done. Now use the simple representation, the non-degenerate representation of the convolution algebra. It's a star-morphism of algebra, as indicated here. Combine it with a Weil quantization, which is defined here. This is a Weil quantizer, and this is a pi, the representation of the convolution algebra, which is also a star-morphism of algebra. And a very simple computation gives you the following property. The star product we are looking for is nothing but the inverse Fourier transform of the convolution product. It is in fact another version of the celebrated twisted convolution which has been introduced by von Neumann almost 1 century ago. And one gets the following expression. Okay? At this level, okay, there is one remark. Of course, one has, for technical reasons, one should work for very regular spaces of function, essentially the Schwarz functions, okay? This, of course, must be extended to larger algebra in order to do physics. One has, of course, to include coordinates, constant, delta, direct function, etc. And this defines what is called a multiplier algebra. And in fact, as far as I know, the most cleanest derivation of such a multiplier algebra is done in this paper. I recommend to read it, okay? It's a very nice paper. Now, being equipped with such a framework, there are other interesting properties which will be used in the sequel. Okay. The first one is that the Lebesgue integral ensures that any action of this type, okay, will be kappa-Poincaré invariant, okay? This simply stems from this general relation. He here is any element of the kappa-Poincaré Hopf algebra, okay? This is proven in this paper once more time. It is a very clean proof, okay? This is a main property, okay? There is another important property which is essential in the following, is the Lebesgue integral is a twisted trace with respect to the star product, okay? One has this type of relationship whenever G goes over, is permuted with F, okay? This is this extra factor which breaks the cyclicity. There is a very interesting property which shows up whenever one has a twisted trace. In fact, such kind of action define a KMS white. It's in fact a KMS state which is not normalized to 1, roughly. It is discussed at length in this paper, and in some sense it is an explicit realization of an old idea which has been defended by Rovelli and also by Kohn while more than 10 years ago. I will not have, unfortunately, time to discuss here during this talk, okay? All of this has been previously applied to reasonable four-dimensional scalar field theory in order to investigate some possible quantum behavior. Some reasonable kinetic operators have been used, which are essentially function of the Casimir operator of the kappa-Poincaré algebra with various interactions. I will be very brief. Globally, the ultraviolet behavior for such kind of radiative correction is found to be rather close to the usual behavior one would find in standard 5-4 theory. More precisely, by computing the the two-point function at one loop with, again, some kind of kinetic operators, one find for various interaction Either no famous ultraviolet infrared mixing, whenever the interaction is of this type, which is called orientable interaction in the liturgy of quantum non-commutative quantum field theory. Whenever the interaction is of this type, which is called non-orientable, some mixing shows up, okay? Divergence is linear in the there is a ultraviolet linear divergence for the two-point function, okay? And now, by performing a cumbersome computation of the beta function, which amounts to evaluate in particular the four-point function, one finds for orientable interaction, orientable models, that the beta function is 0 at one loop. This is reported, for instance, in this paper. Now comes extension to gauge theory. And for practical reasons, one has to supplement these two generic assumptions I gave you in one of the first slides with three more technical assumptions. Namely, we will assume that the non-commutative connection is a connection on the right module, E. This module is assumed, moreover, to be a copy of the algebra describing κ-Minkowski space plus some Hermitian structure, okay? And finally, one has to decide the kind of action of this algebra on the module, and it is taken to be this one. I will comment this last assumption in a while, okay? Now, there is a problem which comes simply from the twisted trace, which is due to the breaking of cyclicity. If you use some untwisted non-commutative differential calculus, you will get some kind of gauge transformation of curvature of this type. And by looking for gauge invariance of, for instance, some action like this, you will get some extra factor like this, okay? And so you will realize that the gauge invariance is achieved whenever this factor is equal to 1, which, due to this unitary condition, amounts to restrict, in some sense, the group of invariance, okay? It's an interesting issue, but it raises many technical questions. This is presently under study. And we prefer not to follow this route, but instead trying to find a way to compensate the effect of the twists coming from the trace. And in such, the question was to find some kind of twisted differential calculus associated with twisted connection and gauge transformation, which was able to compensate the twist from the trace, okay? One, just by perusing the structure of the underlying the problem, one realized that one has to look for twisted derivation first, which belong to the algebra of deformed translation, which means that one has to look for objects which are twisted derivation, so which obey the following twisted Leibniz rule, okay? And in fact, one finds that there is a unique one-parameter family of such twisted derivation, which is given here, okay? And the twists in the Leibniz rule are given here. There is no choice. Up to an overall parameter, which is real, it's gamma here. The proof is given in one of our paper. It's not difficult, just a matter of algebra and combined use of algebraic structures, okay? Being equipped with this, we try to simply extend the very old derivation-based differential calculus to this twisted derivation, and we find such kind of differential calculus. I will be very brief, just flashing the main objects, okay? There is an associative product, which is given by this huge formula, and a differential, which is given here, okay, which is, of course, nilpotent. And the main point to notice is that the differential obeys now a twisted Leibniz rule, which is given here. Of course, one recovers the previous twist from the twisted derivations, okay? And one can show that this triple, this set of data, defines a graded differential algebra. So we have a differential calculus, and we can play with. Okay. So, well, the main point is to define a twisted notion of connection and curvature. I will comment in a while the way to find to carry on the proof. It's rather cumbersome, but not difficult. It is well, it is given, of course, explicitly in the section 2 of this paper. Okay, I will comment it in a while. We find that the twisted connection is given by this expression, okay, with twist here, okay. The related curvature is given by this expression, which can be checked to be a morphism of module, okay. And finally, because we are interested to do physics at the end of the day, we would like to get the field strength. It is defined here, and some algebra gives you the following expression I already gave on one of the first slides. Okay. Next, one has to use to find some twisted gauge transformation, and we find that these are given by this expression, which produce corresponding gauge transformation for the gauge potential, which is given here. Okay. And plug in this into the expression for the F nu gives rise to the following gauge transformation for the field strength, which is found not to depend on the parameter gamma. Okay. At this time, it's time for me to comment the way we did all the proof. Okay. We use the fact that gamma is not a star automorphism. It's called in the mathematical literature a regular automorphism, in that whenever you take the dagger here, you will get a minus sign instead of a plus sign. Okay, it's very important, and in fact, what one has to find, what we needed to find was to find twisted derivations with, in fact, twists which were regular automorphism, in order to be able to compensate the effect of the twist. Okay. Okay. Let me comment the proof. In fact, we proceeded in a very unelegant way, but which had the merit to cover all the possibility. We, in fact, introduced as many twists as possible at the beginning, working component by component. So we introduce for each component, for each twisted derivation, 2 twists. The same for the connection, 2 twists, 2 arbitrary twists, 2 arbitrary twists for the connection, 1 arbitrary twist for each component of the field strength, which resulted in a huge number of a priori arbitrary independent twists. Then we were forced to require 3 conditions: that all these twists were regular automorphism, that the space of connection was were stable under gauge transformation, and that the field strength was a morphism of algebra. This produces a lot of constraints, and at the end of the day, you will get 3 independent twists only. Okay, but fortunately, these 3 independent twists are already known, at least for 2. Among these 3, you will recover the 2 twists which were given at the beginning, which correspond to the 2 twists of the Leibniz rule, and we are done. This reduces drastically the number of twists, and you will get at the end of the day this kind of formula, this one, and this one. Okay, and so we are almost done. Now we have to check if it is possible to have some gauge invariant action. For instance, pick that type of action. Okay. Compute the expression whenever f is gauge transform, and you will get some extra factor, this one given in red here. And this line is simply, this action is simply gauge invariant whenever this factor, this extra factor, is equal to 1. And now, keeping in mind that E, this object here, is a morphism of algebra, This is a shift provided d equal 5. And in the course of this very simple derivation, simply use the fact that the trace is twisted, and simply use the fact that this one, the twist, is a regular automorphism. And that's all. I mentioned a way to have a very much simpler expression simply by using form. In fact, this can be extended to a map given here, thus introducing the one-form connection. It is defined here. The same can be done for the curvature, which is given here. With it's a two-form curvature, and this letter obeys some Bianchi identity, twisted Bianchi identity, which is given here. Now we can simply comment the classical features, okay, of the result we have obtained. So the main result is the following. Oh, I'm sorry. Okay, here we go. Assuming the 5 assumptions, 2 structural assumptions plus 3 technical assumptions, which were given just previously, one finds that the kappa-Poincaré invariant gauge theory on this kappa-Minkowski space, having the physical commutative limit, must be 5-dimensional. And we find that it is essentially the gauge invariance which fixes the dimension of the space and which selects a unique twisted differential calculus, which is suitable for the construction. In short, in fact, starting from kappa-Poincaré and gauge invariance, almost all is fixed. Okay. I will not comment coupling of fermions. Simply use this type of covariant derivative. Okay, it's completely obvious. There is a salient prediction. There is the existence of one extra dimension, unfortunately, and so one has to get rid of it. Now one should notice that the non-commutative gauge invariance holds only in 5 dimensions. If one moves to 4 dimensions, for instance, this gauge invariance cannot be realized. In fact, we started to study one prototypal compactification scheme, 4 dimensions, to get some effective action in 4 dimensions, and in fact we expect to have very small departure from the usual U1 electromagnetic gauge invariance, and so we expect to maybe to get some very stringent bound on the 5-dimensional deformation parameter of kappa. Okay. For the phenomenological feature, well, we try to explore very, very basic phenomenology which could be related to this kind of gauge model, assuming, for instance, a very simple compactification on this kind of orbifold. We assume a kind of scheme which is similar to what is called in the physics literature universal extra-dimensional models, which are characterized by such kind of relation which is very simple to obtain, which is simple, a scaling relation in some sense, in which this, our 5-dimensional parameter of kappa is identified with the bulk, the 5-dimensional Planck mass, okay? In fact, if one uses recent LHC data, there is a lower bound on such extra dimension, which is given, for instance, in the particle data book. I pick it in this book, and one can find this extra dimension should be related to an energy scale of the order of 1 TeV. And assuming now that the Planck mass is of the order of the usual value, okay, 10 to the minus 19 GeV, one obtains this kind of very conservative bounds. There is a very few assumptions, apart from assuming that all the scheme of universal extra-dimensional model is okay, and one finds this bound. One also finds that dispersion relation for photons is deformed. It is given here. It simply stems from the fact from the kinetic operator, which appear in the gauge theory, combined with which is completely fixed. The kinetic operator, there is no choice. Everything is fixed. and one has simply to have to expand it in the parameter 1 over kappa, and one finds such kind of dispersion relation. And now one could, in fact, use this deformed dispersion relation for photon to and combine it with recent data stemming from gamma reversed. Okay, and one would, of course, improve this conservative bound by some order of magnitude, which would, in fact, predict a very, very small extra dimension. There are some problems with this extension. One problem is discussed in one of our paper, which is in fact related to the notion of causality. Actually, the notion of causality is not unique on kappa-Minkowski space. One can define several, at least two. Driving some conclusion from this confrontation may be ambiguous. Sorry?
Oh, excuse me, so you are getting close with your time, so you...
Okay, I am almost done, okay. 5 minutes is okay? Okay, let me go back to the assumption 5, okay? One can say, okay, could we modify the value for D? Could we escape the D equal 4 value for D, at which, for which one has kappa Poincare and gauge invariance? So one could try to modify the action of the algebra on the module. In fact, one can try to twist it, and we have examined this possibility, and we find that, unfortunately, there is no way to modify this action in order to modify the critical dimension for this theory. This is given a paper which will soon appear. Well, unfortunately, I will not have time to discuss the BRST algebra, but all the algebraic framework is discussed in this paper. Okay, there are two. In fact, essentially two Slavnov operations, and this usual one, is the one which is relevant for computation in quantum field theory. And using this, we have fixed the gauge as usual, and we have computed some one-loop correction to the gauge invariant action. It's a standard computation which is rather easy due to the fact that that our star product is very convenient, and the computation is rather standard, and we have found this kind of non-vanishing. There is a non-vanishing one-point function, okay, which simply signals that the vacuum is not stable against quantum fluctuation. And that non-commutative gauge invariance is radiatively broken. To conclude, well, there is among others, some open question we are working on presently. We would like to escape this constraint D equal 4, and it seems to us that there is at least one twist which is missing in the present framework. And we have undertaken some study by replacing our notion of non-commutative connection by connection defined on a bimodule, thus changing one of the main technical assumptions. It's not unrelated to this question, and there is a work in progress. I stop here. I would like to thank you very much again.
Okay, thank you. Thank you very much for the interesting talk. And maybe there is time for one quick question. Okay, so Paolo, please.
And I appreciate your talk, and I would like to know whether this twist that you are introducing touch the wedge product of the forms, And also, I would like to know if among all the consistency you require in order to bring the number of possible twists, constrain it to 3, as far as I understood, you also consider the effect that the covariant derivative has to satisfy a Cartan equation with the contraction operator. So introducing the contraction operator, this I expect has also to be twisted due to Cartan formula for the exterior derivative, and henceforth also the covariant derivative. Thank you.
Okay. Somehow this question and answer part really work. Don't know. Maybe we continue with next talk, and but yeah, Jean-Christophe, are you there still?
Hello.
Yeah.
Can you see my screen share?
Okay, so yeah, we can, perfect. Yeah.
Okay, I'm sorry, there's some sort of technical problem here.
Yeah,
okay.
we can see you.
But if you can see, I start.
Okay, I guess so. Andre and Paolo, maybe, yeah, you contact Jean-Christophe maybe in some other means and ask him the questions. And we continue with Katrin Meusburger, who is our next speaker. Okay, please go ahead.
Thank you. First, thank you for the invitation. I hoped to participate in person, but unfortunately it was not possible. So I'll try to do my best via Zoom. Okay, what I'm going to talk about is 3D state submodels with defects. This is a joint work with John Barrett that is not completely finished, but near being finished. And yeah, I'll start with some motivation. So the motivation is basically to derive Vero-Barrett-Westbury models, also known in quantum geometry as spin-foam models. They take as data a spherical fusion category and a triangulated manifold with a boundary. And to this data, they associate a linear map from some vector space associated to the boundary to the complex numbers. Especially if this boundary is empty, then we just get a complex number, and it turns out that this triangle is triangulation independent. So we get a manifold invariant that has been used as a model, for instance, in quantum gravity and quantum topology to describe some quantized relativity. It also has been used in other topics, namely in condensed matter physics and in topological quantum computing. And I'll explain in more detail how this works. Now what we wanted to do is to take this and to include some defects. So I'll only give a rough picture. What are defects? Well, defects are some submanifolds that are decorated with higher category data. On one hand, the aim is to get some explicit and simple model for a defect TQFT that one can also use to really compute things and to understand things from a physics perspective. On the other hand, our motivation was to apply this on one hand to describe defects in condensed matter physics models, to really describe them explicitly and with a coherent theory, and on the other hand, observables in quantum geometry. So there has been some work on this where it was shown that defects or some very specific type of defects can be used to describe interacting point particles in 3D Euclidean quantum gravity. This was by Barrett and collaborators. But one also knows that this is not a full picture, and one wants to see how to include more general defects, not just lines, but surfaces, and to understand this in a common framework. Okay, I'll start by explaining the Toraf-Viro-Barrett-Westbury state sums. So first, as I said, one takes a triangulated manifold, three-manifold M, and a spherical fusion category, and to this one associates a complex number. So in the following, I neglect the boundary and just talk about closed manifolds. So the spherical fusion category is just some category that is abelian, C-linear, monoidal, so that means it has a tensor product. Pivotal, that means it has duals, and the double dual is naturally isomorphic to the identity. And spherical, that means it has a notion of traces. There's left traces and right traces, and these two have to agree. And also one asks that it's finite semi-simple, so that one has a finite set of simple objects, and all the objects can be described as direct sums of simple objects. Okay. Now, the simplest example is the representation category of a finite group. The abelian structure are direct sums of representations. The monoidal structure is tensor products of representations. The pivotal structure is just given by the representations on the dual vector space. The trace is just the usual trace from linear algebra, and the simple objects are the irreducible representations. This is not such an interesting example because it gives very bad invariance. Something more interesting is the following. What one can take is the category of graded vector spaces that are graded by a finite group and also involve a 3 cocycle. So that's a map from 3 copies of the group to the invertible complex numbers. And then the objects are the graded vector spaces. The morphisms are linear maps that respect the grading. And the monoidal structure is given by the tensor product of vector spaces plus the 3 cocycle. So the 3 cocycle essentially tells one what the associator looks like. The pivotal structure is then obtained by taking the dual vector space with the inverse grading and the character. And it turns out that the structure is spherical if and only if this character only has values in 1 and -1. So usually one takes it to be trivial. And simple objects are just the graded vector spaces that have the complex numbers in degree C and that have nothing in other degrees. Okay, so this is a little bit about the background that one needs to define these models. And with this data, one associates manifold invariance by constructing a state sum. So how one does this is one labels the triangulation with a spherical fusion category. Each edge is labeled with a simple object, and the edge with the opposite orientation is labeled with the dual. This is what one needs the duals for. Then each triangle has 3 sides that are now labeled by simple objects. And to this one associates a morphism from the tensor product of 2 of the objects to the other. This essentially is done by just associating the dual graph, which gives a trivalent vertex instead of the triangle. One takes the triangle with the opposite orientation, one gets a morphism in the opposite direction, and this is just related to the other one by the trace. And in this way, one associates to each tetrahedron a so-called 6J symbol. So this generalizes the 6J symbols from physics, which are for the representation theory of SU2. Basically, one has 6 edges labeled by simple objects. One has 4 sides that are labeled by morphisms, and one puts them together, as I've shown in the picture here. And in the end, one takes a trace. So this is just a graphical notation for a certain morphism from a given object to itself, and by taking the trace, it becomes a complex number. And this has a conceptual meaning, namely it encodes the associator that describes the associativity of the tensor product on the simple objects. This is all one needs to know how to reconstruct the associator. And one can also show that this 6J symbol is independent of all the choices one has made in between. Okay, and with this data, one constructs the state sum. So one takes the product over all the 6J symbols of different tetrahedra and the triangulation. One multiplies it with the dimensions of all the objects associated to the edges. So these dimensions are just traces of identity morphisms. Then one sums over all the labelings with simple objects and with morphisms. And then in the end, one rescales with the dimension factor times the power of is the number of vertices. And one can show that this is invariant in the sense of it does not depend on the choice of triangulation or any other choice one has made. It's just a number that belongs to the manifold. And how one shows this is by using Pachner moves. So different triangulations of this manifold are related by Pachner moves. So finite sequences of Pachner moves. There's one Pachner move that takes 2 tetrahedra glued along a face and replaces them by 3 tetrahedra glued along an edge. And the second Pachner move is subdivision, inserting an additional vertex in between the tetrahedron, in the middle of a tetrahedron, and connecting it with all the other vertices. And then it turns out that the invariance of the state sum under the 2-3 move, that's the one that's the first one, follows directly from the pentagon relation for the associator, and the invariance under the other move follows from the invertibility of the associator, so that it's a natural isomorphism. And in this way, one gets triangulation independence of the state sum, and one can also extend this to manifolds with the boundary, and in this case, one gets a topological quantum field theory. And I'll just give one example that is a non-trivial one. If one uses a category of graded vector spaces with a cocycle, one gets the so-called Dijk-Graf-Witten models. So in this case, an edge is just labeled by a group element, and the edge with the opposite orientation by the inverse. For a triangle, one just gets the requirement that the product of the group elements of 2 on the edges is equal to the third one. Otherwise, one just gets the zero morphism space. And for a tetrahedron, one gets precisely this cocycle omega. So this is a complex number that depends on the labeling of the edges. And if one now sums over all the group elements, then one gets the so-called Dijk-Graf-Witten model. This is related to the moduli space of flat G bundles on the manifold. So this is like a toy model, but one can see how one gets kind of interesting structures. And this is a very simple example to compute. Okay, so we wanted to use this model and to include defects. For state sum invariance with defects. And what we consider is 3 types of defect. So defect surfaces that are supposed to be 2-dimensional piecewise linear submanifolds, defect lines and defect points. And the latter are some graph on the submanifold. And then one needs first to decide what kind of data one associates to the defects. So to a 3-dimensional region in the diagram, we then in the manifold, we then associate a spherical fusion category as before. And then one has a defect surface that is between 2 spherical fusion category, and to this one associates a so-called bimodule category with a bimodule trace. So that's a finite semi-simple category. One has again simple objects, together with some action functors that describe the action of the 2 spherical categories on this manifold. So this is like the action of an algebra on a module, only that now the algebra is a monoidal category and the module is a module category, and these actions are functors. And then one has 3 coherence isomorphisms that tell one it doesn't matter if one first takes a tensor product and then acts, or first acts with one object and then with the other. And the third one tells one that it doesn't matter if one first acts on the left and then acts on the right or the other way around. So these are coherence isomorphisms, and they satisfy pentagon axioms and they can be viewed as some sort of generalization of the associator in a monoidal category. And then one also takes traces. These are just these are linear maps from the endomorphism space of some object to the complex numbers and have the usual properties of the trace. So they're cyclic, they're non-degenerate, and also in this case, they have to be compatible with the action functors. There's also a procedure that tells me what to do if I reverse the direction of the plane. Then I take just the opposite category with some opposite actions. To a defect line, one then associates a bimodule functor between the two bimodule categories on the sides. So one has a line between two bimodule categories, and to this line one associates a functor between them that is compatible with the action. Compatible with the action means it doesn't matter if I first act and then apply the functor, or first apply the functor and then act. And this is again encoded in two natural isomorphisms, which are called S and T in the following. And these functors also have to be C-linear and exact. And then to a defect point, one associates and I should say, if one reverses the orientation of the line, then there's also a procedure that tells me what to assign to that. If I reverse the orientation, I have to assign the adjoint functor. And to a defect point, one assigns a bimodule natural transformation. That's a natural transformation between the defect functors that label the incoming lines, and it's compatible with the bimodule structure. Okay, this is quite complicated categorical data. I just want to explain it on two examples. The first example is transparent defects, and this gives the center construction. So there I take just an underlying spherical category as a bimodule category over itself. And then the bimodule functors and natural transformations are just objects and morphisms in the center of the spherical fusion category. So this has been investigated before. There's some work on defects in Toraev-Viro invariance and also in Kitaev lattice models, and excitations in Kitaev lattice models. And this was precisely the data used there. So it's important that one gets this as a special case of the general construction. The other case where one can understand it quite well is in the Dijk-Graf-Witten model. So in this case, the bimodule categories are given by sets with the actions of the underlying groups. So I have two categories that are essentially graded vector spaces or consist of graded vector spaces for different groups. And the bimodule categories are just sets with the action of the two groups and the generalized cocycle. Bimodule functors are morphisms of sets with group actions and some generalized one cocycle. And bimodule transformations are quite complicated to describe. But in the case where one has a trivial set with a group action, that means it has just one element, they're related to morphisms between certain representations. So I don't want to go into the technical details of this, just to say one has an example where one can really work it out explicitly. And in this case, one gets things that make sense and that one can also use for concrete computations. Okay, now the question is how to define this model from the defect data. And the idea is that one uses the defect data to construct generalized 6J symbols. And these 6J symbols come about in the same way as the 6J symbols of a spherical category. They are just obtained by considering the associators on the simple objects. And here we do this in a similar way, only we take the coherence isomorphisms for the defect data. So in the spherical fusion category, I have the associator and I get a 6J symbol. If I have a CD bimodule category, I have three different generalized associators that describe the bimodule structure, and I get three different 6J symbols. So I've drawn these 6J symbols colored here. So the black lines and gray lines correspond to the objects of the spherical fusion categories, and the colored lines correspond to objects of the bimodule categories. And one sees diagrammatically, it looks exactly the same, only that some edges are colored. That's to distinguish which category the objects and morphisms come from. And the traces are replaced by bimodule traces. So again, this allows me to give this just gives me a complex number that has similar properties as the 6J symbols for spherical fusion categories. Then one also has coherence data for the bimodule functors. And then one gets even more colors. So one has colors for two different bimodule categories, for a spherical fusion category, and one has these new pink arrows that are for the functor. And this is again just some shorthand notation for a complex number that is very analogous to the one has for spherical fusion categories. And finally, for bimodule natural transformations, there one doesn't have coherence data, but one can encode the natural transformation itself in some kind of further generalization of a 6J symbol. Okay, and all of these things have a diagrammatic calculus that is the same as for spherical fusion categories. So basically, one can do the usual spin network calculus and glue different 6J symbols. The only conditions is that whenever I glue them or apply an identity, the colors must match. Okay, with this one can define the state sum model with defects. So I take a triangulation of the manifolds, and I have defects that are on a submanifold that is transversal to the triangulation. Then that means that the defect planes can intersect the tetrahedra in two ways, either in 3 edges that are incident at a common vertex, or in 4 edges that leave an opposite edge pair empty. Then one basically has different types of tetrahedra. One has the usual tetrahedra, like in a spherical fusion category. So these tetrahedra intersect no defect planes, and then one just gets the usual 6J symbol for a spherical fusion category that encodes the associator. Then one has tetrahedra that intersect the defect plane in 3 edges. These tetrahedra are for a module category or a bimodule category, and they encode the generalization of the associator that gives me the bimodule structure. This has some colored edges and some black edges, so the symmetries become less. And some of the edge orientations are fixed. Then one has another tetrahedron that intersects in 4 edges. There again, one has 2 edges that are from spherical fusion categories, and one gets a 6J symbol that encodes the coherence isomorphism that tells me it doesn't matter if I first act on the left or on the right. And similarly now, I can have tetrahedra with planes that are labeled by lines that have a functor line in between. I get the coherence isomorphism for the functor and the functor 6J symbol, and I can have surfaces that are labeled by natural transformation that I get the 6J symbol for the natural transformation. So to every tetrahedron in the triangulation, I can assign in a very canonical way a certain generalized 6J symbol, which is just a complex number. And then the state sum is defined just as before, only that we use the generalized 6J symbols. So I take the product over all 6J symbols and multiply by the product of all the dimensions of edges, which are defined just as before, only that the data may also come from a bimodule category. Then I sum over all the labelings of edges with simple objects and of triangles with morphisms. And then I rescale this by some dimension factor that takes the dimensions of the spherical fusion categories to the power number of vertices. So this looks like before, only that the 6J symbols are slightly different. Then the question is, what about topological invariance? Well, one has to prove invariance under Pachner moves. So there is a 2-3 Pachner move that relates 2 tetrahedra glued along a face to 3 tetrahedra glued along an edge, and a 1-4 Pachner move that subdivides the tetrahedron. The 2-3-Pachner move again corresponds to the pentagon relations that are satisfied by all the categorical data in the model. So we have a pentagon relation for the associator and the spherical category, for the data that characterizes a bimodule category here, and for the data that characterizes a bimodule functor. They all satisfy pentagon relation, and this gives me invariance under the 2-3-Pachner move. And in case the natural transformations are involved, then this comes from the bimodule compatibility. And the 1-4-Pachner move invariance is a consequence of the invertibility of the coherence isomorphisms. Then one gets a theorem, namely that the state sum is a topological invariant. It depends on the defect data and it depends on the manifold, but it does not depend on the chosen triangulation. And for this, one simply needs to check systematically the Pachner moves. By looking at the different pentagon relations and splitting them into two parts and using the invertibility of the coherence isomorphisms. Then one gets a lot of different Pachner moves. So here I've given some picture of 2-3-Pachner moves that all corresponds to different tetrahedra with defects. And here in the upper picture, one sees that what it does is one has 2 tetrahedra glued along a line, and then one replaces them glued along a face. One replaces them with 3 tetrahedra glued along a line. And here this line can also go through a defect surface now. And one can also have a 2-3-Pachner move where the additional line does not go through a defect surface. One can have defect surfaces that intersect the tetrahedra in different number of edges. So these first two were for a C-module category structure. Then one can have 2 different spherical fusion categories. One get a pentagon relation for a bimodule category structure. Here's another 2-3 move for that. Then one can have 2-3 moves with functors and 2-3 moves with natural transformations. And it's similar for the 1-4 moves. One can subdivide in any way that is possible. So here one has edges that intersect defect surfaces. One can subdivide just as before. Then there's one interesting diagram where one has a little bubble in the middle. There one gets the dimension of the spherical fusion category. One has diagrams for bimodule categories. Everything can be subdivided as before, only that now the additional lines can also go through the defect surfaces. And in this way, one gets a model that again has topological invariance and can be used to describe defect structures. Yeah, and the idea is a very simple one. Tetrahedra correspond to generalized 6J symbols that give the coherence isomorphisms of the data on the simple objects. And the triangulation independence again comes from these fundamental relations that these coherence data must satisfy. Okay, so there were many aspects of this that I haven't commented on for lack of time. I haven't spoken about extending this to the boundary, but this is quite straightforward. One again does it in the same way as one does it for spherical fusion categories. So this poses no obstacles. And then, of course, what one wants to do with this is really consider examples. So first, one can consider the case where one has only defect lines. This gives some similar results as models that were defined more ad hoc using just defect lines. And one can compare with this data, and we have done this, and in some cases, we know that it completely agrees. So this can be seen as a generalization of that. But one can also look at examples with defect planes and compute this explicitly. So the picture for a defect sphere I've given, and one can now admit also data on these defect spheres and evaluate this. And the most interesting example, I think, in this case, or the first example, is to do this for Dijk-Graf-Witten theory and compute some associated invariance, not just of 3 manifolds, but also of 3 manifolds decorated with defects. And we have done this in some cases, and I know, for instance, how to compute it for a lens space with spheres inside that is decorated by some data. And then, of course, in the end, we want to apply this to at least some toy models for quantum geometry and quantum gravity, and maybe some other interesting applications. Thank you for your attention.
Oh, thank you very much for the nice talk. And are there some questions from the audience first? Or maybe some from the online participants? No? Okay, so if there are no questions, thank you again. And now we continue with Dmitri in person. Yeah, please.
Thank you.
Go ahead.
I'd like to thank all the organizers for the invitation and for this opportunity to participate in the wonderful activities of the Corfu Institute. And today I'd like to present results of some work done in collaboration with Igor Bandas, Kurt Lechner, and Paul Townsend. Does it work at the pointer or sorry? Thank you. So the main goal is to present a new theory, which is a non-linear electrodynamical modification of Maxwell theory, which we discovered a year ago. And this theory is unique in the sense that it has all the same symmetry properties as Maxwell theory. In particular, in addition to, of course, Lorentz invariance and gauge symmetry, it has also it is invariant under electromagnetic duality and possesses the conformal invariance. And we know that the duality and conformal symmetry plays a very important role in various areas of theoretical physics. And in general, models of nonlinear electrodynamics have been under intensive study during the decades as possible tests or guides for discovering new physics in various areas, and in particular in cosmology, the models of nonlinear electrodynamics have been used for studying inflation, dark matter, and of course the properties of various black holes. And they all nonlinear dynamics also has applications in condensed matter physics and for describing strongly correlated condensed matter systems and optical phenomena. And let me just mention, of course, the most notable examples of nonlinear electrodynamics, which are Born-Infield theory, which has been constructed for and invented for eliminating the problem of the infinite self-energy of charged particles. And as we know very well, it has very important application in string theory. And then, of course, the effective field theory of quantum electrodynamics by Eller and Heisenberg. Then the most models of nonlinear electrodynamics which we have found in the market has been constructed new models in a somewhat heuristic way, and with the aim to solve specific problems in theoretical physics, but not their construction has not been based on some fundamental principles like symmetry. So though I should mention that there have been several models of nonlinear electrodynamics which possesses conformal invariance, and this has been studied and applied since the beginning of the century, and one can find the review of these models in this paper here. So the natural question we asked was what model or what theory will arise if we impose the requirement that it has the same symmetries as Maxwell theory, and this is what I would like to represent here. But before presenting this theory itself, let me set the notation and convention, set the stage with the discussion of, well, of course, very well-known example of Maxwell theory. So the Maxwell Lagrangian is well known. Of course, it can be written in terms of in a Lorentz invariant way using the stress energy tensor, or in non-manifestly Lorentz invariant form using the electric and magnetic vector fields. The pre-Maxwell equations have the well-known form again. So they are accompanied by the Bianchi identities on the dual of the field strengths of the electromagnetic field, and in terms of electric and magnetic vectors, they have the same, the following form. And of course, we know very well that the pre-Maxwell theory is invariant under conformal transformations, or under the whole conformal group in 4 dimensions. That, let me just mention how the rescaling acts here. So if you rescale the coordinates with some parameter A, and the vector field of electromagnetic field with the inverse parameter, then the Lagrangian can be seen immediately to be invariant under the conformal invariance. Then there is a second symmetry of Maxwell equations. This is the symmetry under electric magnetic SO2 transformations of the field strands and itself. So if we rotate the field strands and its dual in the equations, Maxwell equations, and the Bianchi identity, then of course these equations are not changed. This is the symmetry of equations of motion in this formulation, but one can also construct manifestly invariant, duality invariant Lagrangians for this theory, but this is a different story. Now, if you go to the nonlinear electrodynamics, a general Lagrangian for nonlinear electrodynamics in 4 dimensions can be constructed using 2 and only independent Lorentz invariant combinations of the field strands, which are f mu nu times f mu nu and f mu nu times Hodge dual of f mu nu here. There are the only Lorentz invariants in 4 dimensions which one may have. And of course, in general, this theory will not have neither electric magnetic duality nor conformal invariance. So let's first see what properties of the Lagrangian should be satisfied for having the conformal invariance. So basically, the Lagrangian should be the homogeneous function of degree 1 to ensure the conformal invariance. So if we rescale f squared and f theta squared with some parameter a, then the whole Lagrangian should be rescaled with the same factor a. Basically, this means that the Lagrangian of conformal invariant nonlinear electrodynamics can be cut into the form where it is proportional to the Maxwell Lagrangian itself times some function which is the ratio of these 2 invariants. Then one may ask the question when this theory also has duality invariance. And in that case, one should look at the equations of motion again and the Bianchi identities. Now the equations of motion get nonlinear, so they are expressed in terms of the derivative of the Lagrangian with respect to the field strands of the electromagnetic field. And we require that after rotating these 2 tensors here, sorry, there is the typo here, there should be no derivative here. So we should get the new combination of the field strengths here such that upon the rotation, these new f prime, f tilde prime enter in such a way that the Lagrangian form does not change. And this requirement, first introduced in general by Gaillard-Zumina and then elaborated by Gibbons and Rashid, lead to the following condition on the Lagrangian. So the f tilde should be equal to this product of the derivatives of the Lagrangian with respect to the field strengths of electromagnetic field. And again, the most known example of the nonlinear theory with the duality invariance is the Born-Infeld theory, which I write down here. And then one can see that where T is the dimensionful parameter of dimension of energy density, or it is also known as the tension of the three brane in the context of string theory. And when this parameter goes to infinity, which corresponds to the weak field limit, then this theory reduces to Maxwell theory. But this theory is non-conformal, of course, because the parameter is dimensional. So now the question is, as I said, what will we have if we impose also the conformal invariance? And this leads to this unique theory, which we called ModMax, and ModMax has the following form here. So it consists of two terms, the one which is basically the Maxwell term plus another one which is the square root of the square of these two Lorentz invariant parameters. And gamma here is the dimensionless constant, which actually should be not less than 0 due to the requirement of causality and semi-classical unitarity of this theory. And you can immediately see that when gamma equals 0, then when there were interactions switch off, this theory reduces to Maxwell theory. And this is the only duality invariant and conformal theory of nonlinear electrodynamics which one may have in 4 dimensions. And now let's have a look at its energy momentum tensor. Of course, because of the conformal invariance, so the energy momentum tensor is proportional to the Maxwell energy momentum tensor times the scalar factor here. And of course, because again, because of the conformal invariance, so the trace of this tensor is equals to 0. Now you see that there is a subtlety here, because now we have non-analyticity in the definition of the energy momentum tensor. And so let's discuss this non-analyticity in more detail. So you see, if you look at the energy density part of the energy density T00 can be written in this form. So we have the ambiguity for all electromagnetic field configurations for which E squared minus B squared equals 0 and E times B equals 0. These are fields which are called null electromagnetic fields, which satisfy these properties. And of course, we have the ambiguity in the definition of energy momentum tensor for these fields, which runs from -1 to 1. But surprisingly, one resolved this ambiguity going to the Hamiltonian formulation of this theory, in which these fields, now fields are well defined. So in the Hamiltonian formulation, of course, the energy density is just the Hamiltonian density of the theory, which one can obtain by this Legendre transform from Lagrangian to Hamiltonian formulation. In the Legendre transform, we introduce the momentum conjugate to the electromagnetic field, which is called electric displacement vector, and which is the derivative of the Lagrangian with respect to the electric field here. And to perform the Legendre transform, we should invert this equation and express the electric field in terms as a function of the field D and the magnetic field B, substitute back in this equation, and then we have the Hamiltonian. And the Hamiltonian has the form which is very similar to the Lagrangian form of this theory. And now what we see that in the Hamiltonian formulation, the electric magnetic duality is manifest. It just rotates the fields D and B, and all the Hamiltonian is manifestly invariant under these rotations. Now, let's look at the equations of motion. So how this problem of the null fields is resolved. Let's look at the equations of motion in the Hamiltonian formulation, which have this form now. They are also called macroscopic electromagnetic equations here. They express B and D, the time derivatives of B and D in terms of the electric field defined as the derivative of the Hamiltonian with respect to D, and another field H, which is the derivative of the Hamiltonian with respect to the field B. And it turns out that for example, if we are considering the plane waves, which satisfy these null conditions here, so of course, then we find that for the plane waves, or for any, I would say for any null fields of this kind, these conditions require that the following relation between the electric displacement vector and magnetic field B. And for these solutions, the Hamiltonian, in particular for the plane waves, is just the modulus of the Poynting vector, if you wish. And it turns out that these solutions, and in particular the plane waves, exist only for gamma, which is greater or equal to 0. And the general solution for the plane waves is, of course, well known. So we can write it down as the real and imaginary part of the two constant amplitudes multiplied by the exponent of the wave configuration here, where k is the plane wave momentum. And as an example, so the simplest possible solution for the plane wave is the linearly polarized wave when d times b equals 0, and the electric field is related to the displacement tensor by a factor of this parameter gamma, and there is a standard relation between the electric field and the magnetic field, which are orthogonal to each other. But the point is that in spite of the fact that e squared minus b squared equals to 0, d squared minus b squared is not equal to 0. So in the Hamiltonian formulation and inside the equations of motion of the Hamiltonian theory, these are well-defined solutions. Now, let me go to another property of this theory, which is birefringence. And it is known that in the case of nonlinear electrodynamics, these theories present so-called birefringence phenomena, which consists of the fact that if one considers the propagation of electromagnetic waves in some homogeneous electromagnetic background, then due to the polarization of light in this with respect to the background electromagnetic field, the light splits into two rays which take different, in general, geodesics characterized by different dispersion relations of this general form. So we have omega squared equals k squared times lambda plus, where lambda plus minus are some coefficients which are called refraction coefficients, which depend on the wave vector of the propagating light, and also depend on the, for example, in the case of the magnetic field, on the form of the magnetic background field here. In the case of ModMax theory, it turns out that one of these modes propagates in a standard way along the standard relativistic light cone, while the second mode has the following dispersion relation. This dispersion relation depends on the angle between the wave momentum and the direction of the magnetic field, but it does not depend on the amplitude of the magnetic field. And the reason is that the theory is conformal. So because of the conformality, there is no dependence on the value of the magnetic field here. And now one can compare these properties of birefringence with other theories. Okay, thank you. So we now learned that in the case of linear Maxwell theory, there is no birefringence. Then the birefringence is also absent in the case of the Burning field theory. It's almost unique. Well, it's unique physically relevant theory where there is no birefringence. Now, if you look at the elder Heisenberg or effective QED, then the effect of this birefringence, the difference between lambda plus and lambda minus, can be is estimated just by calculations, and it should be of this form: 4 times 10 to the minus 24 times the b squared, where b squared is the value of the magnetic field here. Now, and for ModMax, if we look at the mode which propagates orthogonally to the magnetic field, then the effect is 1 minus e to the minus 2 gamma here. And the recent experiments which have been fulfilled for example, in the laboratory of Linyara of IMFN near Padova, which is called the P-Vlas experiment, they impose the following bounds on the possible values of the birefringence index, which now has this value for the magnetic field of 2.5 Tesla. So they have not been able to measure their idea was to measure the birefringence, of course, of the QED, but because of still this ambiguity, the effect has not been measured. But they expect that in the nearest future, they may use some more powerful magnets of CERN to improve their measurements. And in principle, but these results may show what is the value of this parameter gamma if this theory has something to do with reality, if you wish. But in this case, one should also take into account the combination of, say, ModMax contribution to the birefringence and quantum effects, if you wish. Okay, then let me just say some words about possible generalization. Well, some applications which has appeared during this year of this theory in cosmology. So there have been several papers which studied the effects of ModMax theory in the case of black holes, like non-strom, tau-NAT, thermodynamics of electrically magnetically charged black holes. And let me here only give the simplest example of how this theory modifies the solution, for example, of the Rydberg-Nordstrom black hole, which is electrically charged. So we couple this theory to gravity via its energy momentum tensor and find that the Rydberg-Nordstrom black hole metric has, of course, this almost standard form where the function R has the following dependence on the mass and the electric charge of the black hole. But here there is this factor of e to the minus gamma, which deforms this solution and which tells us that the relation between the mass and the charge of the Rydberg-Nordstrom black hole gets modified by this factor. So basically, since I have said that the gamma should be positive always, then there is a kind of screening effect. So in the case of the extremal black hole, for example, we see that the mass can be effectively mass squared can be effectively less than the physical electric charge. Then people have considered also more complicated cases of charged black holes, as I said, like tau-NAT, tau-Bolt solutions and all that. Let me just quickly say 2 words about generalizations. There exists a generalization of Born-Infeld theory, which includes ModMax, and the Lagrangian of the theory has this form. So if I have shown you the Lagrangian for the Maxwell, for the standard Born-Infeld theory, where basically, which is obtained by putting here gamma equals to 0, but this is the modification of the Born-Infeld theory, which remains duality invariant, and which reduces to ModMax theory if we take the tension of this theory to infinity. This is one generalization. Another one is in 10 dimensions. So there is a generalization of self-dual chiral two-form theory for the abelian gauge two form with a 3-form gauge potential, which on the mass shell is self-dual, and the Lagrangian has this a bit complicated form because in this case we need to introduce some auxiliary field to make this Lagrangian Lorentz invariant. I don't have time to give the details, but just to say that this theory reduces by dimensional reduction from 6 to 4 dimensions again to ModMax theory. Then just mention that there is an n equals 1 supersymmetric generalization of the theory where and the Lagrangian has been constructed independently by Sergei Kuzenko and by our group, but I don't have, I think, time to discuss this in details. So let me just pass to the conclusions. And so I have tried to present this new theory, which is unique and because of its maximal symmetries similar to Maxwell theory. It has generalizations in higher dimensions. As I said, the parameters should be greater than 0 or equal to 0 in the Maxwell case, of course. And this is imposed by the properties of unitarity and causality. There are plane wave solution which is non-trivial here because there is this non-analyticity point in the theory. There are recently people also have found in this paper some topologically non-trivial Hopfian and knotted solutions of electromagnetic field in the theory. Then there is this birefringence effect, which can be used to test this theory experimentally if we wish, and there are supersymmetric generalizations. And as a further development, it would be interesting to study in more details the properties of the theory and couple it to charged sources. Very interesting problem is the quantization of the theory, which probably can be done, I think. And then the question of whether and how this theory can be embedded into modified gravity theories and study the relation with string theory and application in cosmology. And I think that a very promising development is the consideration of the applications of the theory in condensed matter and the optical physics as an effective theory, and in particular via the gravity CMT correspondence. So I'll stop here. Thank you.
Thank you. So thank you very much for this very interesting talk. Questions, please. Hello.
Just a couple of questions. First, when you write your Lagrangian in terms of spinor indices, so with self-dual and anti-self-dual combinations of the field strength, does it take a simple form? That is more revealing, perhaps?
Probably.
You understand, with F alpha, beta, F dot alpha?
Yes, yes.
You haven't tried?
Well, we have not done this, but probably it may have some, it may have some suggestive form, probably. Okay. It's more related to the complex structure, if you wish,
because
right?
The square root, under the square root, you have this combination that.
Yeah, there might be, because let me just say, I don't know exactly how it looks like, but what I wanted to say is that, for example, this combination is just as a for example, as a cosine of the phase of the complex combination of what you want to construct in some sense.
This would be very, F20 and 02.
Yeah, something like that. Yeah.
Another question is this, is there a way to invent some conformal invariant matter, some medium that would mimic this kind of effect?
Yeah, that would be very interesting to see if, of course, when the theory couples to gravity, if you don't consider the Einstein part, then gravity remains conformal. So coupling to gravity is conformal, but this is only one example which I know so far. But of course, it would be interesting to see what happens.
Maybe for experimental.
Or maybe, I don't know, some limit, some conformal limit might be interesting.
Thanks.
Okay. Well.
Hi. So I also wanted to ask you two questions. One, technical. How do you prove that this is the uniqueness of such a solution, whether it's order by order in power of FF bar, or well, which is the technique you use? And then I would be interested in understanding more about the possible physical applications of such a theory, phenomenological.
Yeah. Okay. Well, the first question is technical. So it's not order by order proof. It's the complete solution of two conditions. The first condition is this one, so that any conformally invariant Lagrangian should have this form. So this should be some general function of the ratio of two invariants. And then the duality invariance imposes this condition, which I wrote in a somewhat probably. Yes, and then I just solve these two conditions. So I impose, I take this and I substitute here. And you find that there is a unique solution of this equation. And Probably I can explain in more detail this, but well, its unique solution modulo the requirement that the theory reduces to Maxwell theory. There is a second solution, but there is a second unique solution, which is so-called Bilanitsky-Birula conformally invariant electrodynamics, which is obtained by taking the tensionless limit of Born-Infeld theory. This is the only other solution, but it does not reduce to Maxwell. Yeah. Then there was a question about applications. The applications I expect interesting implications might be via this IBS-CFT holography, for example, for the description of kind of mod insulators where the nonlinear effects of these electrodynamics can mimic the current interactions in the condensed matter system. So this is one of the possible applications where via nonlinearity effects, one describes how the electric currents in a certain material interact, which properties it has. One of the possibilities.
Okay, Gaetano.
Thank you. It's very interesting. My question is related to Paulus. Can you explain better what is the philosophy behind requiring invariance and duality? I mean, since the equations of motion or of electrodynamics, because of sources, are not duality invariance. So at least as far as we know, and because we don't know of monopoles. So what is the philosophy for looking for duality?
Well,
motivation. Yeah.
The question may be, if you wish, philosophical. The first one, just or purely academical. What, from the theoretical point of view, what theory can one construct which has the same properties as Maxwell theory, free Maxwell theory, and which has all its symmetry? This is a general question of which might be not related to physical application. But then, of course, the question is, what can we do with the theory when we couple to the sources? If we couple to the charge sources, of course, in nature, we don't see monopoles, but of course, in the theories like string theory, the monopoles and dipoles, they present always, and the duality gets generalized to the case of the theories which include also electric magnetic sources. This is one thing. Then another thing, one might speculate on the possibility of using this theory in the case of monopoles and dions, which have been found in spin glasses, if you know, as a quasi-particle states which mimic very well the Dirac monopoles in spin glass systems. And again, this theory in principle might be used for the effective description of this kind of quasi-particles.
Okay.
Okay. Maybe we shall continue with the next speaker. Which is Philip Haida. Is he around? Okay. Okay, so he's supposed to be here. Yeah. Okay, so oh yeah, please. Okay. So let us have a long coffee break.
Yeah.
All right. Yeah. So we meet again in like 25 minutes. 11:20. No.
Maybe email.